And here we go. All right, so last time we were talking about molecular geometry, molecular shapes. Let's just take a step back in time and rehash some of those. So 3D molecular shapes, 2D molecular shapes, it all starts from a Lewis diagram. If you draw a shape where you end up with two pairs of bonds, that's a linear shape. If you have three bonds, and this is something that would happen when you have, say, boron in the center, or if you have like a double bond somewhere, then that's trigonal planar. If you have two bonds and one lone pair, that's bent. If you have four bonds, that is tetrahedral. If you have three bonds with one lone pair, that's trigonal pyramid. And if you have two bonds and two lone pairs, that is bent. So basically, there's 1, 2, 3, 4, 5, 6, if you count this separately. There's 6 different shapes that you will have to know and be able to identify for a molecule after you've drawn the Lewis diagram. Okay? So, let's talk a little bit specifically about the polarity of bonds and how that applies to molecular shapes. So, we know that if you have two identical atoms, the electrons are equally shared, right? So, anytime the atom is the same. So let's say a bromine atom bonds with a bromine atom. This is a nonpolar covalent bond, and the way that we figured that out is because we looked up the electronegativity, and I don't have my periodic table in front of me, but whatever the electronegativity of bromine is and whatever, it's going to be the same number minus the same number. So your delta En is equal to 0, right? So nonpolar covalent bond is here. Okay, then if you have different atoms bonded to each other, like let's say we had a hydrogen bonded to the bromine, these are going to have different electronegativities. So the delta En, let me just grab a periodic table. We got 2.8 and 2.1. So your difference is 0.7. So there is a difference there. Okay, so there's a difference there. That means one atom is attracting the electrons in the bond more than the other. So this is a polar covalent bond. The electrons are being pulled closer towards bromine. Right, the one with the higher value always pulls in that direction. Okay? All right. When that happens, because one of the atoms is pulling the electrons more, that creates what we call a partial charge. And the partial charge is symbolized by the Greek letter delta. So delta, it looks like in a kind of like an eighth note, a curvy eighth note, if that makes any sense for you musicians. Okay, the D, like that. Just kind of practice drawing it. It's a funny looking D, right? So that's the delta, and that means partial charge. So, because the electrons are pulled more to one side than another, going back to this HBr example right here, I'm going to put a delta, but I'm going to put a minus sign next to that delta because that indicates the electrons are being pulled towards that end. And on this side, we put a delta, but we put a positive because the electrons are being pulled away from that end. So I'm going to modify my highlight here and redraw this. So if the electrons are being skewed towards the bromine, imagine it kind of being spread out asymmetric. Oh, that's too big. Like this. That orange shading represents the electron density, where the electrons are being pulled more, and they're being pulled more towards bromine, always towards the higher electronegativity. All right, so let me show you just another example or two of that. Let's see. even something like this, like nitrogen bonded to hydrogen. In this bond here, nitrogen's electronegativity 2.5. Nope, it's 3. It's 3. Hydrogen is 2.1. So again, we have a polar covalent bond. The electrons attracted more towards the nitrogen than the hydrogen. So I'm going to draw two deltas. Which side is delta negative? The N. And the hydrogen is the delta positive. So are you guys okay with doing that? Two atoms, one with higher electronegativity gets the delta negative. Okay. All right. This term dipole, dipole is referred to a bond that is polar, right? So if we know how to look at a bond, a single bond, and determine if it's polar, in a molecule, a lot of times you have many bonds. And so how these bonds are arranged can have an effect on the total molecule. So we're talking now about the polarity, but now we're talking about polarity of the molecule. So let's start simple. In a diatomic molecule, if we go back to something like chlorine, this bond here, the electronegativity is the same, so that means there is no dipole. No dipole because the left side and the right side are exactly the same. There's no delta negative, no delta positive. Does that make sense? Everything's equal on both sides. Okay. So this is what we call a non-polar molecule. Every side has equal electron distribution. This is the simplest molecule there is, 2 atoms. Left and right exactly the same. Okay. Let me give you another example. Say BeF2. I drew this on the board the other day, but let's just draw it again. Okay, so this one looks like this. Beryllium, fluorine, fluorine. Let's take these bonds one at a time. So the electronegativity of beryllium is 1.5. Electronegativity of fluorine is 4.0. That's a big difference. This is one example where if you calculate it, delta En, which is 2.5, would suggest that this is ionic. But remember how I said sometimes, even though the number qualifies as being ionic, sometimes the bond is not ionic? All right, I'm not expecting you to know when that is. I'm just telling you in this example, it's not ionic, okay? So what we have here is a polar covalent bond. And the electrons are very much pulled in the direction of the fluorine. So if I'm going to draw some deltas on here, the beryllium would be delta positive, the fluorine would be delta negative. Actually, you know what? It'd be very delta negative. I'm going to draw that bigger. Delta negative. Does that picture make sense so far? Okay. So the delta negatives, are they exactly opposite from each other? What is the angle between the B, the F, the B, and the F? It's 180. So that means this dipole in this direction and this dipole in this direction are equal but opposite. Which means that they cancel out. So if I ask you the question, which side has more electron distribution? What would you say? Neither. And that means that this molecule is non-polar. Now, specifically, what if I asked you, you know that bond between BE and F right here? This guy? This bond here, didn't we say that that was a polar covalent bond? We did. So I have a molecule that has a polar covalent bond. Actually, it has two of them. And depending on how those bonds are angled, the effect of those dipole bonds can cancel out. It's just, think of a tug of war. A tug of war between two equally strong teams. Who's going to win? No one. That knot that's in the middle that decides who wins, right? That stays right in the center. That's what's happening here. Okay? So there are forces pulling to the left. There are forces pulling to the right. But neither one is pulling more than the other. That means overall it's a tie. Okay. Let me give you another example. What if we had something like this? You built this one in lab the other day. The electronegativities, 2.1, 2.5, 3.0. If I use some shading to infer electron density in the bond between H and C, do you see how I made it slightly favoring carbon, but not dramatically, just kind of subtly? Well, how come I made it subtle, whereas in the other one I made it like really obvious? Yeah, the electronegativity difference is only a little bit bigger, right? It's not hugely different, right? Okay, and then for nitrogen and carbon, the difference is 0.5. So yeah, they're closer to nitrogen. So what I have here now is two dipoles. Both of these are polar covalent bonds. Now, we need to draw a direction. In the bond between H and C, which one gets the delta negative? The C. And we're going to draw a little arrow. Little arrows always point towards the delta negative. Okay. In the bond between carbon and nitrogen, which one gets the delta negative? The N, right. And the arrow, again, points towards the right. So, in this molecule, I have electrons being pulled more towards the right side than the left side. You guys agree? All right. So that means this molecule is a polar molecule. Because electrons are asymmetrically distributed. They're gathering more on the right side of the molecule than the left. That means this molecule has a partial negative charge on this side and a partial positive charge on this side. Now, this is a relatively simple molecule, right? There's only 3 atoms, right? When they're straight lines, you can look at this and you can figure out your delta ENs and you can figure this out. In fact, we actually don't even need to calculate the delta ENs most of the time, because as long as you see that they are different atoms, you know they have different electronegativities. So the looking up the numbers is not actually that necessary. The point is if there is a difference. And do the differences cancel out, or do they kind of favor one direction or the other? All right. Let's move on to a slightly bigger molecule. I'm going to need more space here. I'm going to add a page. Okay. How about a molecule like this? I mean, it's pretty clear that fluorine and boron have different electronegativities, right? Okay. And I will tell you just, the arrow, the dipole arrow goes towards the fluorine in each case. Think of this as a 3-way tug of war, where the strength pulling in all 3 directions is equally the same. Is there any one side that has electrons more so than the others. Everything is equal, all three sides, yes? Okay. So this is a non-polar molecule. Let's look at another one that's similar to this. We drew this shape in an earlier homework. I have different atoms attached to the center. Hydrogens are two of the bonds. One of them is an oxygen. So if I were to look up the electronegativities, oxygen is 3.5, 2.1, 2.1, whoops. And carbon is 2.5. Okay, so for each of these bonds, there's going to be some direction. There's going to be some dipole. Okay, so carbon is a little bit more electronegative than hydrogen. So when I draw it and I shade them that way, does this arrow make sense? Okay. And then for the oxygen and the carbon, are you guys okay with what I've drawn so far? All right. So just strictly from a net direction standpoint, think of it like this. The forces in my molecule are pulling electrons in the direction of those arrows. So do you kind of see the electrons huddling towards this side, the right side? This is an imbalance, right? The molecule is polar. So I guess what I'm getting at is if there's anything different about one of the sides, anything at all, if it's either a different element or maybe even a lone pair, your symmetry is thrown off. And it's the distribution of electrons will be asymmetrical. That means the molecule will be polar. If there's anything different about one of the sides, right? So let's go back to tetrahedral. Remember the perspective drawing? 4 atoms. So let's say we're drawing this guy, CH4. Okay. Center is carbon, and the outsides are hydrogens. You guys remember the funny bond angle? What is it between atoms in this molecule? Close, 109, 109.5, okay. The angle is 109.5, and it's true for every angle. Every one of these angles is 109.5. If hydrogens are attached in all 4 directions, would you agree that all 4 of these directions are equally spread apart? Yeah. If they are equally spread apart, and if you have the same atom in all 4 directions, is there any one side that has electrons more than the others? No. Non-polar. Is the bond between carbon and hydrogen a polar covalent bond or a non-polar covalent bond? This bond right here in red. Yes, the bond, polar covalent bond, yes. But as a whole, the 4 polar covalent bonds cancel each other out, resulting in the molecule being non-polar overall. And really, at the end of the day, what we need you to do is to figure out whether the molecule as a whole is polar or non-polar. That's the goal. Okay. The next iteration of that molecule was the one that looks like this. So, for example, if this was pH3, this is what that shape would look like. If I have electrons being pulled, well, actually, it doesn't even matter. At this point, if I see that there's a lone pair there, I already know that the balance is thrown off. I don't need to look up any numbers. I automatically know this is polar because there's not a fourth bond that cancels the other three. The last shape, H2O. Polar or non-polar? It's polar. It is polar because it's like this. How are we doing so far? Okay. Let me give you a couple and you tell me if you think the molecule is polar or not. Okay. So, how about this? Is that molecule polar or non-polar, and why? Yeah, this is polar. The electronegativities, the dipoles, do not cancel exactly because it's not the same element. So, technically, let's say I ask you to justify this. All right, you would look up oxygen. You'd say oxygen's electronegativity is 3.5. Carbon's is 2.5. Sulfur. So sulfur is also 2.5. But let's look at how the shading works out. Okay, so do you see how the bond between sulfur and carbon, that's basically a non-polar covalent bond. Everyone see that? Okay, but there is a polar covalent bond. And that means we have a dipole in that molecule that is not canceled. This is polar. How about something like this? But I drew it straight. Doesn't it look like the left and the right side are the same? Oh, what does that mean if there's lone pairs? That means it's not straight if there's lone pairs? It is not straight if there are lone pairs. Because if you recall, whenever there's four pairs, there's no way anything with four pairs can be straight. This is actually a tripod, right? This is actually something that looks like this, right? It's got to be bent. This is polar. What about something like this? Before you answer, stop and think, because you should know something else about this molecule. What else should you know about this molecule? Did I draw it the appropriate number of times? I did not. So I'm only showing you part of the picture. This actually is drawn like this. Is that it? Just the two? There's a third. Okay. If I draw this 3 times, I'm doing that because the double bond is actually averaged between all 3 places. That means the bond strength in every direction is the same. If the bond strength is the same in every direction, is there one side of this molecule that has electrons more than the others? No. So that makes this molecule what? non-polar. Okay. So it seems to me that you guys are getting it. So let's. What did we do? We drew Lewis structures. When I say infer geometry, that means tell me linear, bent, tetrahedral, trigonal pyramid. Tell me the shape, right? Draw the bond dipoles. That's these little arrows. These guys. You always point the arrow towards the more electronegative, right? Look at the symmetry, right? If they are symmetrical, that means these arrows all cancel each other. If they all cancel each other, then we have a nonpolar molecule. But if they're asymmetrical, if they add up, right? If they go uncanceled, that means it is polar. Okay. So take a second and let's just do these. Let's do this guy, let's do this guy, and let's do this guy. Draw them out, the Lewis diagrams, figure out what the geometry is, and tell me if it is polar or nonpolar. Make a cameo appearance. Yeah, that's mine. All right. Well, first, did you guys get structures that match these? Okay, so let's assess our polarity. For ASCl3, that's polar. What is the reason? Lone pair. The lone pair throws off the balance. SiS2, non-polar, because the electronegativity difference in any direction, in the left or right direction, are equal and opposite, which means the net forces are zero. Non-polar. Is this bond right here, is this bond a polar covalent or a non-polar covalent bond? It's a polar covalent bond, and it's okay to have polar covalent bonds in a molecule that's non-polar because they cancel. CH2F2, I have drawn this as symmetrically as I can. It looks like on paper that the left side cancels the right side. It looks like the top cancels the bottom. So therefore this molecule is what? There are 4 bonds. Whenever there are 4 pairs of electrons, are they flat or are they 3D? They are 3D. And if they are 3D, is this really shaped like a cross? It's not. This is a tripod. So if this is a tripod, are the H's directly, are they actually opposite of each other? Are the F's opposite of each other? They're not. This is polar. No matter how straight you draw it as a Lewis diagram, it does not change the fact that 3-dimensionally, these bonds are not directly opposite of each other. And that's the tricky part. Okay, you got to pay attention to the 4-pair family. Nothing in the 4-pair family is actually straight. Okay. All right.